Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from the power system stability, and the name of the topic is application of equal area criteria in that short circuit at one end of the line. Now let us consider that there is a one generator which is G1. It is connected to this infinite bus bar through a double circuit line. So these are the double circuit lines. Now let us say if the fault is occur at point these, I will give this point name as a F. We will assume that the fault whichever will be occurred here, it is nothing but a three-phase fault. Now what happens here because of the fault? I will explain this figure B later on. Now first of all we will see how the P delta curve will be drawn here. So this will be what? First one is nothing but this is your PE, this will be delta. First is the curve which indicates a pre-fault, means when we have both the lines in the circuit. So its corresponding maximum power transfer will be equal to P max 1. It will be equal to what? P max 1. So therefore, how I can write an expression for the maximum power transfer before the occurrence of the fault, or one can say this is the case of pre-fault condition. How I can write here? If you see, these two lines are parallel with each other. Means what? I can say the effective reactance will be equal to what? X1 will be equal to XD dash plus this X1 parallel with X2. X1 parallel with X2. So therefore, we can write the expression as E dash into V upon this will be your X1. This is reactance before fault or pre-fault, which is equal to XD dash plus X1 parallel with X2. So this will be your formula of PE1. PE1 will be equal to what? It is P max 1 into sine delta. Now let us observe that the fault happens at point F. Let's say this is a point F. The fault may be at a generator or at infinite bus side, either side, that is at generator side or infinite bus bar side. Whenever fault occurs at either the end, it actually affects that particular bus bar. As here the fault is near to the generator, so it affects this bus bar. Affects to this bus bar means what? The voltage associated with this bus bar will become 0. The voltage associated with this bus bar becomes 0, and it can be seen like this. This XD dash, it will be separated, it is grounded, and the remaining X1 parallel with X2, it will be separated. Why this is separated? Because there is a fault which occur at point F. So now during fault condition, what happens here? During fault condition, no power will be transferred from the synchronous machine to infinite bus. So therefore, what we have to write? During fault, we can say the power transfer will be equal to 0. So I can write this as nothing but your during fault situation, because here it is assumed that the fault takes place near to the generator. That is, near to the generator means what? On the same bus bar near to the generator. So as the fault occurs, V will be equal to 0, and you know P equal to EV upon X into sine delta. So as your V 0, PE will be equal to what? This is also equal to 0. But as the PE is 0, I can write it as PE2. You know, PA will be equal to what? PM minus PE2. Now this term is 0, means your acceleration will be more positive, and the rotor will accelerate, delta will start increasing, and the synchronism will be lost unless the fault is cleared at a time. So that's why this is, if I show this, this will be the state of PE2, which is equal to 0, which will be along x-axis because it has a value 0. So because of acceleration, your load angle delta will travel from this point delta 0 to, let's say, up to delta C. So I will show it with the names for easy identification. Let's say this is your point A, this will be point B, this is your point C. Okay, I will take this as a point D here, and this will be your point. I can take up to this, or you can take any way up to this. Okay, I will take this up to this point. This is nothing but E. So what happens at point A? As we know, we already discussed this. What happens at point A? At point A, PM0 will be equal to PE1. So acceleration will be equal to 0, speed will be equal to omega s, rotor of speed of the rotor will be equal to synchronous speed, and delta will be equal to delta 0. But as soon as fault occurs, what happens? The voltage will become 0. As voltage becomes 0, PE will be 0, that is PE2 will be 0. PE2 will be 0, and that's why it suddenly drops to the point B, which will be along x-axis. And as your PA is more positive, so acceleration will be there. So your delta will start increasing from delta 0 to, let's say, the point, suppose delta C. Now at point C, what you observe? At point C, suppose the fault is cleared by opening the line number 2. This line 2 is cleared now. Okay, then what it will be? We will have this xd dash in series with x1. So we will get a third value of a reactance, which is called as a post-fault reactance. So at point C, your circuit breaker will operate, and again your electrical characteristic will jump to the point D. Now this will be the curve that is called as PE3, which is a post-fault curve when we have only a first line in the picture. Now after point D, what you observe here? After point D, here PE will be greater than PM. See it. This is your PE, which is greater than this PM. So therefore what happens? PA will be negative, because PA equal to PM minus PE. Negative means what? It will deaccelerate. It will deaccelerate. But still, because of kinetic energy of the rotor or the rotor inertia, the speed will not be lesser than synchronous speed. Okay, it is more. It is more than synchronous speed, but now it starts decreasing. It will slow down. And at point E, you can say, you can take this point, or directly you can take this point also, delta max. At point E, what you observe? It will be equal to what? Here I will take this E point. So it will be equal to, PE will be equal to P max into sine delta 2. Now here delta reduces and speed will try to become equal to synchronous speed, that is omega s. So if you see, what was the formula here for PE3? Now only we have one line. So reactance will be what? Xd dash plus x1. So this is electrical power transfer, a post-fault situation. Pmax, here instead of Pmax 2, you have to write here Pmax 3 into sine delta. So now if you see, we have to write equations for area A1 and area A2. So how we can write an expression for area A1 and area A2? I will write it directly, these expressions here only, so that it will be easy for us. Area A1 will be equal to, limit is what? Delta C 0 to delta C. What is upper limit? PM. What is lower limit? PE2, because PE2 here 0, but lower limit is there, it is PE2. So therefore you can write it as integration delta 0 to delta C PM into d delta, because this PE2 will be equal to 0. And how you can write the expression for area A2? It is but obvious, easy. A2 equal to what? Integration delta C to, let's say, suppose delta 2. So how you will write? Upper limit is what? PE3. So I will write it here as PE3 minus PM into d delta. PE3 means what? It is nothing but Pmax 3 into sine delta. So these are the equations which are associated with area A1 and A2 when the short circuit occurs at one end of the line. Thank you for watching this video.